main objective today is to determine what is exothermic and endothermic reaction. Exothermic reaction are chemical reaction that transfer energy from the reacting molecules to the surrounding. When this happens, the temperature of the surroundings increases, meaning the surrounding get hotter. A common example of an exothermic reaction is combustion, such as wood burning. While endothermic reaction take in energy from the surroundings. As a result, the temperature of the surrounding decreases, so the surroundings get colder. In an exothermic reaction, the product have less energy than the reactants because energy is released to the surroundings. The difference in energy between the reactants and the product is the energy released. This energy transfer is represented in an energy profile diagram, where the energy level of the product is lower than the reactant. Next is endothermic reaction. In this reaction, the product have more energy than the reactant because energy is absorbed. The difference in energy between the reactants and the products represent the amount of energy taken in. The energy profile diagram for endothermic reactions shows the product at a higher energy level than the reactant. That's all everyone. Thank you for listening.
So now we're going to do over potential energy diagram. So let's start with this one. On the left you have the reactants and on the right products. At the top of this diagram we have the transition state, also known as the activated complex. On the y-axis is the potential energy, and on the x-axis this is the reaction coordinate. So notice that the products have less energy than reactants. Whenever you see that this reaction is considered to be an exothermic reaction. Exo means like outside. Exothermic means that heat is released out of the system into the surroundings. So whenever heat is released, the entropy of the reaction is negative. As you can see, the enthalpy is the difference between potential energy of the products and the reactants. So, it's products minus reactants because the products have less energy than the reactants. We're going to get a negative value. Now, what is the energy difference between the transition state and the reactants? What is that called? This is known as the forward activation energy. That activation energy is the energy that is needed to get the reaction started. Without the energy, the reaction will not work. So one way you can reach the activation energy is by increasing the temperature of the reaction, which will speed it up. Now, what is the energy difference between the transition state and the products? This is the activation energy, but the reverse reaction. So if you need to go backwards, you got this way once you reach the transition state. That's when the reaction takes place. So you need enough energy to get the transition state. Now, what's going to happen if you add the catalyst to this reaction? Now, we know that the purpose of catalyst is to speed up a reaction, and enzyme are a biological catalyst that is speed up reaction in living system. How if we add the catalyst, we're going to have a new diagram that look like this. As you can see, the activation energy is lower here. The activation energy is only this high, but before it was significantly higher. So as you can see, adding the catalyst lowers the activation energy, and when you have a lower activation energy, the reaction will process faster, and so that how a catalyst will speed up a reaction. This by lowering the activation energy. Now, we can withdraw the potential energy diagram for an endothermic reaction. if you wish to draw if for an endodermic reaction, you need to draw the products with a higher energy than reactants. So the products have to be above the reactants. And now it's endothermic. So as you can see, delta H is going to be positive since delta H is products minus reactants. If you take a large number and subtract it by a small number, you're going to be a positive. Result for example, 10 minus 4 is plus 6. In the left side, if you take a small number, subtract by a large number, if you're going to get a negative result, like 3 minus 7 is 4. So let's say this is the products is a value of 100. The reactance is at the 300, at the transition state is at 600. So if you want to calculate, let's say, the Ford activation energy. The Ford activation energy is difference between the energy of the transition state and the energy of the reactance. So in this case, that's going to be 600 minus 300. So activation energy for the forward is positive. Now, if you wish to calculate the reverse activation energy, is the difference between the energy of the transition state and the energy of the product. So that's going to be 600 minus 100, which is positive 500. So now if you wish calculate the entropy of the reaction is the products minus the reactants. So the products have a value of 100, that reactants is 300. So because of the products is lower, energy is going to be 200. It's so if you have a two-step reaction, there's going to be two transition state, TS1, TS2. The transition state is also known as the activated complex. So here's the reactants and here's the products and is the intermediate, which is like it's in the middle. So overall, is this reaction exothermic or endothermic?
So what is enthalpy? Enthalpy, often called the heat content of a system, enthalpy change denoted as delta H, is particularly useful in chemistry because many reactions occur under constant pressure conditions. We represent enthalpy changes using thermochemical equations. For example, these equations tell us that when 2 moles of hydrogen gas react with 1 mole of oxygen gas to form 2 moles of liquid water, 572 kilojoules of heat are released. The negative sign indicates that this reaction is exothermic. Interpreting enthalpy changes is straightforward. A negative delta H means the reaction is exothermic, and a positive delta H means it's endothermic. The magnitude of delta H tells us how much heat is either released or absorbed.
Calculate the heat released when 50.0 grams of methane is burned in excess oxygen, giving the following thermochemical equation. This tells us that when 1 mole of methane is burned, 890 kilojoules of heat are released. So, the first thing we do is to convert grams of methane to moles. The molar mass of methane is approximately 16.0 gram per mole. So, moles of CF4, which is methane, is equal to 50.0 grams divided by 16.0 grams per mole, which give us 3.125 moles of methane. Now, we use the enthalpy change from the thermochemical equation. We know that 1 mole of methane releases 890 kilojoules of heat. So, we multiply the number of moles of methane we have by the enthalpy change. 3.125 moles times negative 890 kilojoules per mole, which equal to negative 2781.25 kilojoules. The negative sign indicates that heat is released. Therefore, when 50.0 gram of methane is burned, 2,781.25 kilojoules of heat is released.
Hello there, it's Raven K. Cuevas. And today's topic, the first law of thermodynamics, says that heat is a form of energy, and as what all other forms of energy are subject to, it follows the law of conservation of energy. So what does this mean? It means that heat energy also cannot be created or nor destroyed and can only be transferred to one form or another. Don't overthink this too much. This law is all about heat as energy and follows the law of conservation of energy. And that's it. Now to appreciate the application of this law, let's try a very good example. This cone is just a type of rock, but for scientists, this rock contains energy that produces heat energy when it undergoes complete combustion. Actually, some power plant utilizes this coal to generate electrical energy or what we call electricity. What they do is that they feed this coal into a boiler furnace and with the assistance of oxygen and emitted heat. This creates combustion in a form of heat energy. Now the heat energy will transfer its energy to water above it making into steam. And this steam will rotate the turbine. And that's a mechanical energy right there. And this turbine will rotate a generator which converts that energy into electrical energy. See that just by knowing this law, you can do so much. And that's it. This is Raven K. Performance.
How to solve problems using the first law of thermodynamics. Hello everyone. Today, I'll explain how to use the first law of thermodynamics formula to solve problems involving gases. The first law of thermodynamics states delta U equals Q plus W, where delta U is the change in internal energy of the gas, Q is the heat added to the gas, W is the work done on the gas. Step 1. Understand the signs of heat and work. Heat added to the gas is positive. Heat lost by the gas is negative. Work done on the gas is positive. Work done by the gas is negative. Step 2. Use the signs correctly in the formula. Example, if the gas loses 150 joules of heat and 60 joules of work is done on the gas, the change in internal energy is delta U equals negative 150 plus 60 equals negative 90 joules. This means the gas internal energy decreases by 90 joules, so the temperature decreases. Step 3. Interpreting the change in internal energy. The change in internal energy is directly proportional to the temperature change of the gas. If delta U is positive, the gas temperature goes up. If delta U is negative, the gas temperature goes down. Step 4. Solve for unknowns. Sometimes, you may need to find heat added, work done, or final internal energy using the formula. For example, if a gas starts with 200 joules of internal energy, you add 180 joules of heat, and the gas does 70 joules of work. The change in internal energy is delta U equals 180 minus 70 equals 110 joules. Final internal energy is U final equals U initial plus delta U equals 200 plus 110 equals 310 joules. Step 5. Solving for heat. If given work and change in internal energy, solve for Q by rearranging Q equals delta U minus W. Example, work done on gas is 40 joules. and internal energy decreases by 150 joules. Q equals negative 150 minus 40 equals negative 190 joules. So, 190 joules of heat is lost by the gas. In summary, always keep track of positive and negative signs. Apply delta U equals Q plus W. Use the relationship between internal energy and temperature to interpret results. This method lets you analyze energy changes in gases and predict temperature changes effectively. Thank you.